bigger space. And not just mapped into the bigger space, but mapped into orbits of the bigger space. Because remember, orbits still had those same invariants. So we've taken monic polynomials, whose discriminant is a multiple of p squared for mod p squared reasons, and mapped them into this bigger space so that the first 5 invariants remain the same, and then you have a 6th invariant, which is that p. And we want that p to be bigger than m. So we reduced it to an orbit counting problem. We have a representation of a group, and we want to know how many integer orbits are there, having bounded height and having invariants in certain ranges. And this is where the techniques that we've been developing to count orbits with invariants in given ranges, we can just apply to this problem. So we want the height, in other words, the height of C1 through C5 to be at most x, but we also want this last invariant to be bigger than m. And our methods allow us to count orbits with invariants in given ranges, and we work out what that count is. And we find that the number of G0Z orbits on VZ having non-zero discriminant, height less than x, and Q invariant greater than m. Okay, we knew that we'd get the right answer out of this. We were hoping that it would be the saving that's expected, and it's exactly what the geometric sieve would have given had it been a codimension 2 condition. So the moral really is that once you change a mod p squared condition to a mod p condition, even if it's not codimension 2, it's happening kind of morally for a codimension 2 condition. It's a codimension 1 condition that's multiple. So you still get the saving somewhere or other. If you get the actual count, it will be right. But changing mod p squared conditions to mod p conditions is really key. Okay, so we do that orbit count, and we get the saving we want. And so the corollary is that the number of monic integer polynomials to degree 5 having non-zero discriminant, height less than x, and discriminant to multiple p squared for mod p squared reasons for some p bigger than m is big O of the total count divided by near 2. And the reason is just that because the things that we're counting in the corollary were mapped into things we're counting here. And that's exactly, the latter corollary is exactly the kind of estimate that's needed to complete the square-free sieve on the discriminants of degree 5 monic polynomials. But of course, there's nothing special about the degree 5. We could have made those matrices for any n, and so that completes the proof of the square-free sieve polynomial discriminants. And then, in the case of, that's the statement of the theorem again. You get about 36% of polynomials have square-free discriminant. And as I said, Lenz's conjecture is strictly weaker because you have to sieve less. And so that also implies Lenz's conjecture that the density of F that's a Z bracket X mod F of X, the ring of integers in Q bracket X mod F of X, is 6 over pi squared. Okay, I'll stop there. Thanks so much. Thank you. Yeah, so far it's always been that one additional. Just because of the nature of the problem, we isolate a p that the p squared is dividing it. Usually that p ends up being the additional invariant. Either that happens, or you just get a codimension 2 condition where Ekerdal applies. But this is the first case, this polynomial discriminant case was the first one where we didn't get something explicitly codimension 2, but we could still use orbit counting to get the saving. But one or the other happens. Yeah, we've done many polynomials now using this, but it's not a systematic method yet, in the sense that I don't know if you ask the question on which polynomials does this method apply, I don't know how to answer that question. But on the other hand, many polynomials of interest for which we needed square-free values. So another place where this arose, suppose you have some family of curves, and you want to know what is the density of semi-stable curves inside that or those that have discriminant that are square-free. That's a question that often arises, and we needed that for the Selmer group sieves, for example, when we worked with Weiho. We needed to know that in a certain family of curves, we had the correct density of square-free discriminant curves, so that we could sieve to semi-stable curves, for example. And somehow adaptations of this method have always worked. And we've always been able to do it. So there's always some kind of transformation that you can do or lift it somewhere so that you split apart those p's and then you're able to do the square free sieve. That's kind of an algebraic geometry question. What is the nature of the polynomial so that the places where you become a multiple of p squared for mod p squared reasons, is there some kind of algebraic geometric way of splitting those p's by a suitable change of variables so that you can apply either Ekadal or some kind of other counting method. But splitting apart those p's, it seems like in all the cases that we've ever landed so far, we've been able to do it. The question is, can it always be done, or what are the classes of polynomials for which this method works on? And that I don't know, but it has worked on many other examples. Oh yeah. Yeah, that density can also be worked out by similar methods because it's only one Euler factor that's changing, only one place that's changing, and the sieve only requires the large primes. So any such question can also be answered by this, although I don't know the constant yet. Yeah. Once you can do square free, absolutely cube free. I don't know the constant offhand, but any strictly weaker sieve can also be done. Or that involves the same sieve for sufficiently large primes. Right. Right. And I don't know. As I said, any polynomial that we really needed to know the density of square free values, we worked hard enough, long enough. There was some transformation that we always found that